Okay, kids, it's time to log on to some logarithmic equations. So what we've done in the first part is we solved a bunch of exponential equations, and we use logarithms to do that. So what we're doing here is we're kind of doing the more pure form of it, where we're solving just straight up logarithmic equations. It's a very related concept. In fact, sometimes it's almost easier because some of the hard work's been done, but we do have a few other things that make it just a little bit trickier. Domain restrictions are one of the big ones. So what we're going to do is we're going to look at this property first just to understand how we can solve log equations very easily. So I'm just going to zoom way in here. So this should seem like a very familiar property because this reminds us a lot of the exponential equation property, where if you get two things that have the same base, then you can equate the two exponents next to equate them to each other. So this says that if we're taking the same base logarithm of both x and y, then we can ignore the logarithms and say x is equal to y. So this is a pretty easy to use formula, and if we can get our logarithmic equations looking like this, then we can always drop the logarithms. One thing I'll just notice here, and I'll be pointing this out as we go through and we're doing more examples, it's really important that we have one log on the left side and one log on the right side. It's going to be very tempting from time to time when you have something like log of x plus log of y equals log of z. It's going to be tempting to say, let's just cross out all the logs and say x plus y equals z, but that is absolutely not allowed. So we'll do some examples where that comes up, but just to be clear, that is not the case. It's not like you're dividing both sides by log. So the general rule of algebra, where you can do this and then cross them out, that's not what we're doing. We're simply saying that if you logged something and it was equal to the log of the other thing, well, then whatever you're logging has got to be the same thing. Anyway, more on that later, but just to be aware, this is the property we're going to use, but just you always have to know its limitations. Okay. One other thing that makes this a little tricky is that logarithms always have domain restrictions. So the first thing we're going to have to think about whenever we're solving a log equation is what are your possible what is the possible domain of answers, and do you get extraneous roots? Because anytime you have a domain restriction, you got to make sure your solution actually falls in the acceptable range of values. Okay, so domain of logarithms. So we've talked about this quite a few times before, but let's just bring it up one more time. Log base b of x. X has to be bigger than 0, right? You cannot take log of something that is 0 or negative, and you also have to make sure that b, the base of the logarithm, is bigger than 0, and it also cannot be equal to 1. When multiple logarithms are in the same equation, you're going to determine the domain for each term, and then you're going to choose the most restrictive conditions, and that's going to set the domain for the entire solution set. And this is similar to when you're doing square roots. If I was to do root x plus root x plus 1, let's say, is equal to, I don't know, I'm just going to make something up like 5. We can say the radicand has to be x is bigger than or equal to 0. But in this case, x plus 1 has to be bigger than or equal to 0, which means that x has to be bigger than or equal to negative 1. So each radical gives you its own separate domain. But which one is more restrictive, saying numbers have to be bigger than 0 or saying numbers have to be bigger than negative 1? And it turns out this one is more restrictive. So the overall domain restriction here would be x is greater than or equal to 0. And we don't even have to worry about this because it's less restrictive. So we're going to do something similar with logs as well. Hoping you remember all that stuff from radicals, I guess, last year. If you don't, well, there it is. Okay, so well, this is interesting. Okay, so this says example number 4. Now, I think this was before I split this up into 2 parts, so this is the first example today, but I guess it's the 4th example of the whole thing. So determine the domain of each expression. So this is usually pretty simple. The first thing you better do is you got to make sure that the bases are not variables, because sometimes they will be variables. Since the bases are not variables, we don't have to worry about domain restrictions for them, but we do have to make sure that this business here is bigger than 0. So what we can do is we have to say x plus 2, the entire argument must be bigger than 0. And it can't be bigger than or equal, it's strictly bigger than. For this one, we would say x minus 1 is strictly bigger than 0. And for this one, we would just say x by itself is bigger than 0. Which one of these is more restrictive? So if we actually work this out, this becomes x is bigger than, we move the 2 to the other side. This one will add the 1 to the other side, and then this one there's nothing to do. So of these three here, which is the more restrictive domain, saying numbers are bigger than -2, bigger than 1, bigger than 0. And it turns out that if numbers are bigger than 1, they're automatically bigger than 0, and they're automatically bigger than -2. So this is the most restrictive value or domain. Therefore, we would say for the entire equation, x better be bigger than 1. So if this was an equation and I'm solving it, any value of x that is not bigger than 1 would be extraneous. Okay, this one here. So now we've got x in the base position and we've got it in the argument position. So we've got a few things to do here. So for this one, log base x, remember the base must be bigger than 0, and the base also cannot equal 1. Here, just the argument is bigger than 0. And here, the base is bigger than 0, and the base cannot equal 1. Okay, so we've actually got three different sets of things here. So let's have a look at what's going on. I don't like leaving it as x minus 2 is greater than 0, so I'm going to move 2 to the other side. So basically what I have here, basically what I have here is, I'm going to have to do something with this one as well. Move 1 to the other side. Okay, so you've always got to get x isolated. This one here, I've also got this as a restriction, and this one, I'm actually going to add 1 to the other side. X cannot equal to 2 would be another restriction. So I've actually got 5 restrictions here. I don't need to come what's the word I'm looking for? I don't need to write all 5 of those out. I just need to grab the most powerful restrictions. So between the inequalities, x is greater than 0, x is greater than 2, x is greater than 1, this is the most restrictive. Numbers that are bigger than 2 are automatically bigger than 1 and 0. And I also need to consider x is not allowed to be equal to 1 and x is not allowed to be equal to 2. But it turns out that if I'm saying x is bigger than 2, then these are already included. So all of these, where's my change of color? All of these here, these are included in x is greater than 2. So are these. Same thing, these are included in x is greater than 2. So therefore, overall, it's fine if I just say all values of x are bigger than 2. That will cover all my cases. Okay. Now, one thing I should mention, I don't have an example of it right here, but sometimes you'll have a situation where you'll run into, so this is just a theoretical thing. I'm just going to make something up here. This is a theoretical example here. I probably should think of one. Maybe I'll add that in the future, but for now, I'm just thinking about it. If you had something like, let me come up with something here. Log of x plus 1, and then you had log of 1 minus x, let's say. This could be another situation here where you've got, let's see, so this one would be x plus 1 would have to be bigger than 0, and this one would say 1 minus x would have to be bigger than 0. In a case like this, what you'd do is you'd still isolate x. You'd say x would be greater than or equal to -1. Now this one's a little tricky. I'm going to move x to the other side. So the 1 is going to stay on the left and x is going to move over here. I don't really like how that looks. I'm going to say x is less than 1. A little reminder that when you're solving inequalities, if you divide both sides or multiply both sides by -1, you flip the inequality. So in this case, I added x to the right side so I don't have to flip. If I moved 1 to the other side and I divided by negative to get rid of that, I would flip the inequality. So here I've got these two cases. Now, which one's more restrictive? This is saying x is less than 1, but this is also saying x is bigger than -1. Okay, we don't really have a situation here where we're overlapping so much. We'd actually have to keep both of these. And on the number line, what this is ultimately saying here, well, we'd have to have everything bigger than, everything less than 1, okay, everything less than 1 would work, and we'd have everything bigger than -1. And what we'd have is we'd have this little range of solutions in the middle where x has to be between -1 and 1. So we'd actually have to think of how we could combine them, because what we need is we need to have a set of solutions, or a domain interval, however you want to say it, where the x's satisfy both of these. So it would actually be x has to be greater than -1 and less than 1. So this would be like the overall. And it's even theoretically possible that if maybe these signs were flipped and it said x was bigger than 1 and x had to be less than -1, if that was the situation, you actually couldn't have some value of x that satisfies both of them, and you might actually have, there's no possible solution. That's maybe pretty uncommon, but it is a thing that you might want to think about. That's sort of a trickier concept. We're not too concerned with that at the moment, but just be aware. If you have two totally separate domain restrictions, you're going to have to actually think about how you're going to combine them together to make one set or one interval that makes both parts, like both log parts, happy. Okay, anyway, if it sounded like it's getting a little complicated, that's because maybe it is, but I just want people to at least know that sometimes you do have to put some pretty serious thought into that. Anyway, in your textbook, I doubt they're going to throw that at you too much, and I probably wouldn't either. Okay, so let's look at example 5. This is a pretty straightforward solve for x situation. Log blah, 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 plus log something, something equals something, okay? So what we do to solve these kinds of equations, first thing we do is we do have to pick out our domain. Okay, so we're going to look at this first one. It's log, you don't see a base, so we understand it's log base 10. And then we have, let's see here, so this will be x plus 3 better be bigger than 0. So that says x is bigger than or equal to -3. Okay, that's the domain restriction for the first one. This one here, this says just x is bigger than 0. So when we're looking at this, what is the overall domain restriction for the question? Overall, which one is more restrictive, saying numbers are bigger than -3 or they're bigger than 0? We're going to say x is bigger than 0. That's the overall domain restriction for this question. Okay, so how do we actually go about solving it now that we've done the domain restrictions? You're going to use some properties. So in this case, there's a few different ways you can approach this, but the way I would look at this is we've got log of something plus log of something. We can use the product rule or the product law, and we can combine these together to get log of x times x plus 3. So you multiply the arguments together. Now this other side, we could leave it equal to 1, or we could choose to write it as log of 10. So I'm actually going to do it that way because I'd like to show how that property from the very start, this property right here, I'd like to show how this property can be used. And you don't actually have to use this property necessarily. There's other ways to do this, but let's just see here. Okay, because I have log of something equals log of something, and there's only one log. So now I'm going to use the property log x equals log y. Therefore, x equals y. So that's the property I'm using. Now I can write this as x times x plus 3 equals 10. And this should make some sense. Log of something equals log of 10. Therefore, the something must be 10. Okay, so solving this, we get x squared plus 3x. I'm just going to move 10 to the other side here because what I'm trying to do is I'm trying to get myself a quadratic equation. And then I think I can solve this. I think I can. And we're just solving a simple quadratic equation, so this is nothing special. Once you've got rid of the logs, it's just some basic algebra that people should be comfortable with. Okay, so x is equal to -5 and x is equal to 2. Those are my two answers. Now, before you pat yourself on the back too much, you go, yay! You've got to think, are there any extraneous roots? So the extraneous root is this guy right here, because remember our domain restriction was x is greater than 0. So this one is extraneous, since x must be bigger than 0. So it turns out x equals 2 is the only answer. We might call that a real root, or we might just say that's the answer or whatever. Okay. If you want to understand why this is, let's just take a second. Let's go over to Desmos here. Open up the internet. Usually I have Desmos prepared, but apparently I'm behind on my Desmosing. Let's go to school and let's go to Desmos here. Okay, so if we go log of x plus 3, and then we say plus log of x, and we want to see when is that actually equal to 1. Remember, you have to write y is equal to 1. We can see we get one solution here, which is at x is equal to 2. Does it make any sense to say we have another solution, like x is equal to -5? I don't really see how that would be possible. I suppose one way you might consider looking at it is if, yeah, try this. No, okay, well, I don't know. I'm not actually 100% sure why we'd be getting x is equal to -5 as one of our extraneous solutions. You know what I would say? I'm going to think about that a little bit, but if you have a good answer, leave it in the comments below. I'll give you a bonus mark if you can explain where -5 even theoretically came from in this situation. Sometimes you can see by looking at a graph why you'd have an extraneous root. For me, it's not obvious right now. Anyway, there you go. So x is equal to 2 is our real root. Now, I did say there's one other way you could solve this. I'm going to just show it real quick here, and I'm not going to necessarily use this method all the time, but there's a slightly different method. A different method would be when you get to this point here, you get to log x times x plus 3. So you just do the first step, and it's equal to 1. A different method is using exponential form, because some people might actually prefer to do this. So the way you can do this is you can say, okay, this is log base 10 of x times x plus 3 is equal to 1. So exponential form, what this would do for you is this would get you to, remember 10 is the base, it's equal to the exponent, so 10 to the power of 1 is equal to, and then you'd have it like this. And then you'd solve from there. Now you'll notice this right here is the same as this. Okay, so what I chose to do is I chose to express 1 as log 10, and then I could cancel out the logs. You can also do the exponential form trick. It's whatever floats your boat, to be perfectly honest. They both work. Nothing else to say. Okay, moving on. Alright, so for this one we have log base 3, log base 3, log base 3. They're all the same base. You definitely want to do a quick little check to make sure that's the case. X plus 6 is greater than 0, which means x must be greater than -6. X plus 2 is greater than 0, which means x is greater than -2. And x is greater than 0. So overall, we have x is greater than 0 is the most restrictive domain. Okay, so now what we have is we've got log something minus log something, and then we've got equals log something else. Okay, I'd love to just cancel out all the logs. Some people are probably going to be tempted, and believe me, I've seen it on tests. You cannot do that. The way you must do this first is we're going to use the quotient, because we've got a subtraction of logs. We're going to use the quotient law, and we're going to go log base 3, do not forget to write base 3, it's really easy to forget that. And I'm going to go x plus 6 on the bottom and x plus 6 up top, x plus 2 on the bottom. Then the other side is this. Okay, so you can't actually write this in exponential form like what I did in green up there, so don't even think about that. You've just got log equals something and log something else on the other side, so these are basically going to cancel, so we'll just drop the logs. Something you never want to do if you're a lumberjack. So we've got x plus 6 over x plus 2 equals x. Okay, so now we have to solve this. This is not a hard thing to solve. You move x plus 2 to the other side, and this is usually the point where I would say this is the boredom point, just because it's just simple algebra that we've done before. No, my mic did not cut out. I just decided to go quiet so you could just enjoy the serenity and beauty of the algebra. Okay, so we got two answers. The reason I box x is equal to 2 is because of my domain restriction. This one is extraneous. Cool. If you're really dying to, like test this out, you could put x is equal to 2 back in the equation, work it out like log base 3 of x minus log base 3 of 4 would be equal to log base 3 of 2. It would actually work out as well. So you can always check your answers. I'm not going to do that just for the sake of time. Okay, here's a slightly different style of a log question. So this one usually makes people have a bit of a heart attack, but I really want to encourage people not to freak out too much when they see something that's different. Remember, you've got 3 basic rules. You've got the product, well, maybe you've got 4. You've got the product law, the quotient law, the power law, and the change of base rule. So when I'm looking at something like this, I see there's a variable right there. So first of all, it's in the base. So we'd say x is greater than 0, and also x cannot be equal to 1. Remember, the base cannot be equal to 1. Okay, so now how do I get that x out of there? There's a few ways you can do this, but the way that I would actually prefer is I'm going to look at log base 2 of stuff equals 1, and I'm going to use exponential form to get rid of that first outer log. So I can say that log base x of 9 is equal to, and then it's 2 to the power of 1. So the base is 2, and the exponent is 1. So by doing that, we can get rid of this outer log, and you can always use that to get rid of this log here. You can't do it for the inner log quite yet. Okay, so now we've got this. At this point, you might even consider using exponential form again if you like, or you can do the change of base rule. It's sort of up to you. I'm going to probably use the, it's a tough call, but I'm going to try exponential form one more time. So what this says is the 9 stays put, x becomes the base on the other side, and 2 becomes the exponent. So y equals x squared. If you do it this way, now we've got square root. Don't forget the plus or minus when you're doing square roots with variables, so we've got plus or minus 3. We have the restrictions that x must be bigger than 0 and x cannot be equal to 1. So what we would say is x equals 3 is the only real answer. The negative 3 is extraneous. Okay, so that's probably how I would go about and solve this. Is there a different way you could solve it? You betcha. A slightly different method would be from this point here, you could have used change of base. This unit's pretty interesting because there's just so many different approaches you can take to solve logs. So you could have written it like this. And in this case, this would become log of 9 equals 2 times log of x. The power rule actually allows us to bring that up there. So that would be x squared. And because we have logs on both sides, we can drop the logs and so on, right? So this is an alternatively. You can do this method as well. So just a different way of doing things. Okay, but don't be afraid to sometimes use clever methods like what I did, exponential form 2 times. It's easier. So go ahead and do it that way. All right, we've got one more here. You might want to take a second, see if you can do this. This looks really intimidating. In fact, the fact that you've got x in the base you've got log x, and then you've got 100 times x. Seems like too many x's and almost seems undoable. Take a second and see if you can actually work this one out, because it's quite satisfying if you can. Maybe pause the video and give it a shot. If you're completely stumped, well, I'll just show you. So the first thing I'm going to do is I'm going to look at this. I'm going to go, okay, well, I got x in the base, I got x over here, and log x. This is really problematic. So what I would do is I'd still approach this the same way that I would approach any kind of problem. So if I have a variable in the exponent position, I'm going to take log of both sides. So I'm going to go log of x to the log x equals log 100 times x. So the reason I do this is simple. It looks like I'm making the question more complicated, and I sort of am, but now I can bring this log x to the front. So the exponent comes to the front, and then what I'm left with is just log x. Now this is interesting. I picked this example here because I wanted to show something. Now this is log x times log x. Do not write log x squared. That is not the case. What it is in brackets, you've got the entire log x, and that's all squared. Now, if you're getting really excited because you think you can just cross the logs out, you can't, because the log is squared. If the log is in the brackets, you cannot do this. That is not a thing you can do. What you can do at this point is you can realize you've actually kind of got a quadratic equation here. So what I'm going to do is I'm just going to erase this, because log of 100 times x, this can be expanded by using the product rule. And now we're simply going to make a substitution here. So this is a bit of a trickier kind of question, but I wanted to show this just because it's kind of a neat one. I've seen it in some textbooks and stuff. I'm going to replace log x with something. How about y? If I actually make this substitution here, I can see that we've got a quadratic equation. This becomes y squared. Log of 100, it turns out that's actually just a number. That's just 2, right? This isn't any weird substitution. That's just the fact that log base 10 of 100 is 2, and then this becomes y. So this is kind of a clever little question where we wind up having this kind of quadratic. So we've got y minus 2 and y plus 1 equals 0. Okay, so from here on out, we have y is equal to 2, and then we have y is equal to negative 1. Now we're not quite done, because remember what y is. So y is equal to log x. So this converts into log x equals 2, and this converts into log x equals negative 1. How do I actually get the x's out of this? Well, what I can do here is I can say that, let's put this in exponential form. So this is log base 10 of x equals 2. So 10 squared equals x. And this becomes 10 to the power of negative 1. So 1 over 10 equals x. So what we would finally end up with is x is 100, and x is equal to 1 over 10. Do these satisfy the domain restrictions? Now I realize that I didn't do my domain restrictions quite yet. So looking at this x down here, there's no domain restriction. Or is there? Oh, maybe there is actually. Never mind, I take it back. This is the base of an exponential. The base of an exponential has to be greater than 0. And if you remember from way back when, it's actually not cannot be equal to 1. Sorry, it's this guy here, because this is not the base of an exponential. This is no domain restriction. It's 100 times x. That's just like in any algebraic thing. It's just a polynomial, right? So there's no domain restriction. This x in here, it's the argument of a log, so that has to be x is greater than 0. So when I'm looking at this, I can see overall what I have. X cannot be 1, and x must be greater than 0. So both of these satisfy the domain. So both satisfy the domain. X is greater than 0, x cannot be equal to 1. So they're both real answers. Okay, that's a pretty heavy duty question, but I kind of like that it's just a little bit of a different style here. Most of the questions are going to be like parts A and B, but I like to throw in some other ones just to be a little different. Okay, so one thing you might do just after such a complicated looking question is you might actually check your work. I haven't been doing it for the other ones, but I'm just going to do it for this one because I want to show that it's kind of neat. And hey, there's always the chance I screwed up. So let's just check. X is equal to 100. So is it true that 100 to the power of log 100 is equal to 100 times 100? So if you realize 100 to the power of, what's log 100? That's 2. And then, of course, the other side, well, 100 times 100 is 100 squared. They are the same. It passes. And let's check x is equal to 1 over 10. Then what I'm going to do is I'm going to go 1 over 10 to the power of log 1 over 10. Is that equal to 100 times 1 over 10? Well, what is log of 1 over 10? That's the exponent to which you must raise 10 to get 1 over 10. So that is negative 1. 100 times 1 over 10 is 10. And it turns out that 1 over 10 to the power of negative 1 is 10. And that's equal to 10. It checks out. So that's a fun little question. A little bit of a different guy, but that's one of the trickier log ones. Okay, so anyway, I guess that's it. I guess you can now log off the internet. Thanks for watching.